Welcome to this class on fluid mechanics, and we will continue our discussion on integral flow analysis, and mainly I will be looking at some of the subtle points in the momentum equation and also some examples of the momentum equation. As we recall, for a control volume, momentum equation is given by sum of the external forces on the control volume is equal to d by dt of the volume integral of V rho dV plus integral on the control surface V times rho V dot n dA. So, this is the force equation. Now, before I move on, let us look at some terminology. And if I am looking at subsonic flow, that means flow where speed is less than speed of sound. Then if there is a geometry like this, where we have an expanding geometry. So, this expanding geometry where velocity at the inlet is V 1 area A 1, velocity at the exit A 2 and velocity is V 2, area is A 2, and this is an expanding geometry. This is called a diffuser, and in a diffuser what we find is that clearly as long as the flow is incompressible, V 2 is less than V 1, and if we use Bernoulli's equation, we will find P 2 will be greater than P 1, and so diffusers are devices which are used to slow down an incompressible or a subsonic flow, and the pressure of the fluid will increase as it passes through a diffuser. And opposite to a diffuser is a device called a nozzle. In a nozzle, area decreases along the flow direction. So, here we have inlet velocity V 1, area A 1, and the outlet we have velocity V 2, area A 2. Of course, the shape need not be linear, it could be some function, but it is a monotonically increasing or decreasing area. If it is decreasing, then for subsonic flow this is a nozzle, and here what we will find is for subsonic flows V 2 is greater than V 1 and P 2 is less than P 1. So, now this is a nozzle and a diffuser. If we look at a force due to the fluid on a nozzle or a diffuser, or it could be some other geometry. So, in this case, let us first focus on nozzle or diffuser. This we will do later. If it is a nozzle or a diffuser of the type which we have shown, the force is due to two factors. One is the change in magnitude of the momentum. The fluid at entry velocity is V 1, at exit it is V 2, and V 1 is not equal to V 2. So, there is a change in momentum magnitude, and this change in momentum at inlet and outlet will cause a force. Second cause of the force, if you look at the force equation, this is the force equation, sigma F external is equal to the the unsteady term plus the influx and the outflux term. Now, one entry and one exit mass flow rate is the same, but this V is different, and this is what I talked of, that the momentum of the fluid coming in and the momentum of the fluid leaving are different in magnitude. So, therefore, this term is non-zero, and there is another non-zero term, and that is because of the external forces. So, the second cause, I had said here that there are two causes, and the second cause, first factor is the change in magnitude of the momentum, and the second factor is change in pressure. Since P1 is not equal to P2, this will also cause a force, and these two, the variation of pressure, this comes in the F external term. Together they will decide what is the net force on the momentum or the nozzle. Next, we talked of other geometries. In other geometries, a third cause could come, that force could also come due to a change in the direction of momentum. In the simple geometry shown earlier, inlet and outlet were in the same direction, but if inlet and outlet, the direction is different, then you will observe that there will be a force, because the vector momentum is a vector quantity, and if directions of inlet and outlet are different, that will mean momentum is different, and in this case you will also get, so there will be a net force on the control volume because of the change in the direction of momentum. So, for example, if you have flow in a constant area pipe, this is area A1, velocity V1, area A2 which is equal to A1, and velocity is V2. So, now by continuity equation, if A1 is equal to A2, V1 is equal to V2. So, the magnitude of the momentum efflux is the same, but we look at the direction of momentum at 1 and 2 are different, and this will cause a force on the pipe because of the fluid flow, even if the pressures are the same. Pressure could also cause a difference, but just the momentum itself, even though the magnitude stays the same, the direction on it, the change in the direction is what causes the force. Okay. So, now let us look at one example. Let us look at the example of a diffuser. Diffuser in which flow enters with velocity V1, the gauge pressure at 1 in this section. So, this is section 1 is P1 gauge and the area is A1. Its exit is to atmosphere. So, therefore, the pressure is P atmosphere. the area at the exit is A2 and the velocity here is V2. Now, what we are given is areas A1, A2 at inlet and outlet are given. Now, this is of course mounted on the some count. So, this is given, areas are given, P1 gauge is given and V1 is given, and we are asked to find how much is the force exerted on the support how much force is exerted on the support by the diffuser. Okay, now it is also given that the weight of the diffuser is equal to W, and this includes the weight of the diffuser as well as when it is filled with water. So, that is also included in the weight W, and we want to find how much is the force on this support, because if such a this much of force should the support should be able to provide, otherwise it will break. Okay. Now, in a problem like this, the question is, how do we choose the control volume? Do we choose a control volume consisting only of the fluid, or do we choose a control volume which can we choose something else? And one of the guiding principles here is, if the force which you need, if you choose a control volume in such a way that this force comes in directly as a part of this control volume, or the negative of this force comes as a part of this control volume, then you should choose a control volume like this. So, what we do is, we choose a control volume. Let me now show this. So, this was our problem, this is the flow, this is this, and this is mounted on the ground. So, what I do is, I choose a control volume like this. So, this control volume encloses, I have chosen a rectangular control volume enclosing the full diffuser, and it cuts the support as shown. So, we choose a control volume which is just encloses the diffuser and shows here. Now, in this control volume, what is happening? What we have is, in the control volume, we have flow coming in with velocity V1, this is area A1, and the pressure is P1 gauge. Let us talk of gauge pressures. At this end, flow is crossing here, velocity is V2 and area is A2, and P2, this, so this is 1, this is 2, P2 gauge is equal to 0. Okay. So, these are the different quantities I have named. Now, all this area outside is P atmosphere. But now, if I look at this control volume, the control volume is cutting this surface. So, if it is cutting this surface, the surface, the support, it is cutting the support. So, let us say the support exerts a force R, which I will take it as a vector, I can write it as R x I plus R y j on the control volume. So, when I take a control volume like this, the only cut comes at this point where the support is cutting, and therefore, there I have to put an external force. The other thing which I do is I show my coordinate axes x and y. So, now if I look at this control volume and start solving my problem, the first thing which I get is, if I use mass balance or continuity equation, then I will get minus rho V1 A1 plus rho V2 A2 is equal to 0, and from here I will get V2 is equal to V1 A1 over A2. And this, on this control volume I have applied the mass balance. I have not gone through the details, but it is fairly obvious that this is what it is. The unsteady term is 0, and so is the 0 is equal to d by dt, and these are the two terms which I will get when I expand the integral Cs rho v dot n dA term. So, this is what and in all problems, please remember, the first equation when you do, when you solve these problems, you should first use mass balance. It is the most basic equation with the least assumptions. So, it has to be satisfied, otherwise you could end up making mistakes. Now, secondly, to apply the force balance, let us see which are the external forces on the control volume. So, this was my control volume, which are the external forces which are acting. Now, the gauge pressure at section 1 is P1. So, clearly one thing which is acting on this control volume is the surrounding pressure from all around. That is one external force which is acting. So, external forces, first one is pressure. Any other external force which acts on the control volume, clearly the other one, since the weight is not negligible, it is given to us, is gravity. And then the third one is the reaction R. These are the three external forces which are acting on the control volume. Now, to find this force due to pressure, so to find A, what we can say is P atmosphere all around cancels. So, what we are left with is P1 gauge times A1, and this acts in the I direction. Suppose if this was not a jet, if outlet was not like a jet and P2 gauge was given, then F external due to pressure would be equal to P1 gauge A1 minus P2 gauge A2. So, this would be the net external force on the control volume because of pressure, but now because P2 gauge is 0, we do not count that. Okay. So, this is what it is, and the other one of course we said was weight and this. So, total external sum of external forces, totally we can write it as P1 gauge A1I minus Wj plus Rxi plus Ryj, where Rx and Ry are forces exerted on the control volume by the support. Okay. So, now given this, we have got the first term, then now we apply, we look at the momentum equation. The momentum equation, let us look at it. The x component is sigma fx is equal to d by dt integral Vx rho dV plus integral on the control surface Vx rho V dot n dA. And similarly, in the y direction, sigma Fy is equal to partial by partial t volume integral of Vy rho dV plus integral on the control surface Vy times rho V dot n dA. Now, we are talking of steady state flow because flow is not changing with time and a fixed control volume. So, therefore, the d by dt volume integral term is 0 because we have steady state and a fixed control volume. So, we are left with only the integral Vx or Vy rho V dot n dA. Okay. So, therefore, now we have to evaluate these surface integral terms. Now, for this, as we discussed, we make a mental note of the control volume and we look at its surface and we see at which position in this surface is the fluid crossing the surface. So, this integral on the CS, there are two contributions from 1 and 2 because fluid is crossing the control surface only from there. So, now if we look at integral on the CS Vx rho V dot n dA, this will be equal to, now let us do for surface 1 first, Vx is equal to V1 which is in the positive direction, rho V dot n dA is equal to minus rho 1 V1 A1. So, this is the contribution from surface 1. From surface 2, velocity in the x direction is V2 and it is rho V2 A2. Now, obviously, we are able to do this because this velocity is not changing with area. So, therefore, we are just able to take these as simple simple integrals are taken out and we are integral dA just becomes the area. So, therefore, this becomes equal to, and we can write it as minus rho V1 square A1 plus rho V2 square A2, and sometimes you can, as we have seen earlier, you can write it as m dot times V2 minus V1 where m dot is equal to rho V1 A1 or rho V2 A2. This comes from the continuity equation and this we will be able to do only if there is one inlet and one exit, otherwise we have to keep this form of rho V1 square A1 or maximum we can write it as minus of V1 times M1 dot plus V2 times M2 dot and so on if there are more inlets and exits. If there are only two, then we know M dot has to be constant. So, once we have this, now we substitute everything. So, what we will get is R sub x, I am writing the x component plus P1 G A1 is equal to m dot times V2 minus V1. So, Rx is equal to m dot times V2 minus V1 minus P1 gauge A1. So, this is Rx and similarly when I write the y equation, then Vy is equal to 0 on 1 and 2. So, integral over the control surface Vy rho V dot n dA is equal to 0. Note this is not 0, V dot n dA is not 0, but Vy is 0. So, therefore, we get this. If it was a curved type of if it was a structure which was bending at an angle, then Vy at the exit would not have been 0, it would have been the velocity times cos theta or sin theta and Vx also would not have been V2, it would have been V2 cos theta or sin theta. So, this is what we have for the y component of the equation for the right hand side. So, y component of the equations just gives us Ry minus W is equal to 0, something we would have expected from statics that whatever is the total weight will be Ry and this gives us Ry is equal to W, and this W also includes the weight of the water. So, now the problem looks complete, but there is one more last step to be done. So, we have got R is equal to Rxi plus Ryj. We have got this in terms of given quantities, but notice this R is the force on the control volume. So, the force on the support will be equal to minus R. The problem asked us for force on the support. So, that would be equal to minus of R. Now, notice we took this control volume. Somebody else could have solved this problem, and I will just show you how this will be not so easy. Suppose if somebody decides to solve the problem using only water or this fluid which is flowing as the control volume. That means the second person has a control surface which has the shape of the diffuser. So, now here what will happen is, if this will only contain weight W1, I will say, of the control volume will be rho times volume of the diffuser times G. It will, this control volume, the weight of this control volume in the second choice is only the weight of the fluid. The pressure on this side, we talk of P1 absolute times A1 is the force due to pressure, and P2 absolute times A2 is the force of the pressure on the other side. So, on the control volume, if I draw the external forces on the control volume. The external forces are W1, then P1 absolute A1 and P2 absolute A2, and P2 absolute for the given problem is nothing but P atmosphere. And what we say is this whole diffuser, this applies a force F. F is the force the solid applies on the fluid, and we call it as, maybe let us use the subscript W, force on the water which is applied by all the surrounding this thing. So, now when you use this equation, what you will get is F W plus P1 absolute A1 I minus P2 absolute A2 I. This is the total external force, and then there is minus rho volume times G. This is in the J direction. These are all the external forces on this alternate control volume. This will be equal to m dot times V2 minus V1 along the I direction. This will be the net this thing, and what you will be able to get from here will be Fw. Now, the problem has asked you to find force on the support, whereas what here find here is force on the water inside the diffuser. If you take a minus of this, minus Fw, this is force exerted by water on the diffuser, but this is not equal to the force on the support. So, to get force on the support, you have to draw free body diagram of the diffuser plus support without water. So, you have to now carry out this extra exercise. So, you have this diffuser surface on which from inside minus Fw force is being exerted. On these two sides, P atmosphere is exerted, and we have this support, and when you cut this, you are cutting the support. So, R, the force by the support is there, and there is also W2 weight of the diffuser alone. And then you do force balance on this, and what you will see is P atmosphere which is acting, because this part has already been accounted for in P1 absolutes. So, this P atmosphere when this acts, so you will, the net effect of this will be P atmosphere acting on A2 minus A1, because horizontal components of P atmosphere, the vertical components will cancel out, and the horizontal component will give you P atmosphere multiplied by A2 minus A1, and that when you add up, now if you find the R, you will get the same answer, but this one, the second approach is much more needs a second free body diagram and a second body to be accounted for. When we chose the control volume by including the whole diffuser, this part was automatically accounted for. So, we saved this exercise by choosing a smart control volume. Now, there could be other problems where flow, let us say, comes in here. This is called a turning vane. In a vane, what happens is flow changes direction, and here, so this is a solid plate on which flow comes in like this, velocity V1, area A1, and pressure throughout here is atmospheric. So, this is a turning vane in which fluid is coming in and it changes. A1 is equal to A2, V1 is equal to V2, and pressure throughout and this we can show once we do Bernoulli's equation. If we apply Bernoulli's equation between the two ends, we will get this. Now, here if we have to find the forces on the support, then there will be no force because of pressure. If we neglect the weight, then what will happen is, if the weight is there, then we account for it, but now the main term is the momentum, a flux term, integral V rho V dot n dA. Well, mass balance will tell us V1 A1 is equal to V2 A2, and if A1 is equal to A2, this will give us V1 is equal to V2. Now, let us say this angle, the turning angle of the vane, this turning angle is given to be theta. So, now in the efflux term, we have integral V rho V dot n dA. So, this has to be calculated on surface 1 and surface 2. On surface 1, velocity is equal to V1 I, and rho V1 dot dA will be minus m dot, okay, where m dot is equal to rho V1 A1 and is also equal to rho V2 A2. On surface 2, that is, this is the inlet, this is the exit, this term V rho V dot n dA will be equal to, so this is V1 I, this will be equal to V2 cos theta I plus V2 sin theta j and multiplied by m dot. And the net, when you add these up, you will get the net, this thing sum will be equal to m dot times V2 cos theta minus V1 I plus V2 sin theta j. So, this will be the net effect on the vane because of the momentum efflux in a case like this. So, here the force is coming because of a change in direction, and you will be doing a simple experiment in the lab where you will see this. But one of the key things which one has to remember in all these problems is that mass balance is of key importance. And to illustrate this, let us look at a phenomena called the wake. Suppose we have a cylinder or any body in uniform flow which is extending up to infinity. So, this could be, so we have uniform flow at infinity of capital U in the I direction. Actually, this is nothing but if a plane is flying in still air and if the plane is moving to the left with a velocity u, this is the same problem, but we have just changed the reference frame, and if we fix it on the cylinder which is moving with capital U to the left, if I sit on that frame, then I will see this is the reference frame for a still cylinder. So, this is what we have, flow past a cylinder. Okay. Now, what is observed is, if I go far below this cylinder and I observe the velocity profile, what I find is if I measure the velocity here, the velocity, if this is x, this is y. So, here velocity u or Vx is a function of y, and the velocity just behind the cylinder far away is less than capital U, and after some distance it becomes equal to capital U. So, this is called, this region where the velocity deficit is there is called the wake behind a moving body. Of course, we have inverted the reference frame. So, now we see the body is still, and this is what is called as the wake. Now, one of the problems we could be asked to find, given this velocity profile, find the drag force on the cylinder. Now, to do this, I will talk a bit about this. I will not solve the full thing for you, but I will do some of this and then leave with you with a thought of how to do this. But let us see, certain assumptions have to be made which at this stage will be given to you, especially if it is a part of an exam problem. But what you have to understand is in real life you will have to make assumptions like these, and then maybe do an experiment to verify that the assumptions which you made were right or wrong. And one of the assumptions which is given to you is that the pressure far away here is P atmosphere, and in the we are sufficiently downstream. So, the pressure on this side is also given to be P atmosphere. Now, this assumption for your purposes will be given to you, but you have to start when you solve problems like this, when you encounter them in a new problem for the first time, you have to think of assumptions like these to solve these problems. Such assumptions will give you some estimates. Those estimates may be slightly off mark because these assumptions may not be as what you have expected them. But that is how we solve engineering problems, and that is the crux of integral flow analysis, that we make some sort of assumptions and try to solve the problem. The other thing what we find is that at the distance or height vertically above and below, or this could be actually everything could be in a horizontal plane. So, wherever far away on this side also the pressure is P atmosphere. Now, if you have to find the drag force on this cylinder, that is the problem given to you. So, this is the problem which is specified. It is told to you that you assume pressure is P atmosphere far away all along. The velocity profile at the start at the left end is uniform capital U constant. On the right hand side it is a function of y which is given to you, but it is also given to you that after some height h which will be given, the velocity becomes equal to capital U. So, maybe we will assume a linear profile or some other sinusoidal profile which will be given, or maybe if you have to assume a general profile, then you can work out the constants. If this U is given to you, the other one you know is capital U, and if the height is known to you. So, now the velocity becomes capital U. So, you have to find the drag force on the cylinder. This is the problem. So, then you have to now ask what sort of a control volume do I choose to solve a problem like this. So, let us draw, this is the problem. We know far away here velocity is equal to capital U, which is constant. Downstream, this is the velocity profile. The question said find the drag force. What is the drag force? Drag force is force in the direction of flow. So, for example, if the body was moving to the left, then drag force would be the one which would retard the movement in the of the body in the direction in which it is moving. So, in the direction of flow or opposing the direction of flow, the force is called drag. If it tends to stop the body, it is called drag. If it tends to help the body in moving, this is called thrust, and this force is force applied by the surrounding fluid. So, if you have to find the drag force, what we do is, let us see how to choose the control volume. We choose a control volume which just is outside the cylinder here, because now what will happen is the cylinder will exert force F on the control volume or Fi on the control volume, and the drag force will be equal to force on the cylinder. So, this will be equal to minus F of I. So, on the control volume we say a force F of I is exerted by a cylinder on the control volume. Now, in this case, what is the other end? Inside we have chosen the control volume like this. On the outside we will choose a control volume, because we know pressure far away is all uniform. So, we choose a control volume which is like this, which is a rectangular shape here, a symmetric control volume, where the velocity, so what we have is the pressure is P atmosphere all around, and this height of the control volume we can say is 2h, because after this the velocity has become capital U. So, whatever will come out this side, it will become equal. Okay. Now, I can call this surface 1, I can call this surface 2, and I can now apply the momentum equation, pressure forces will cancel out, only external forces Fi in the x direction, and I can work out and get my answer. The cap u of y is given to me, this is given. So, I can integrate this to find the efflux term on 2. I can integrate this efflux term here will be nothing but minus rho u1 square times 2h times w, where w is the dimension perpendicular to the paper. So, that is what the rho u square, this is the term which I will get in the momentum equation for this surface 1. So, integral along the control surface Vx rho v dot n dA on surface 1 is Vx is capital U and rho v dot n dA is minus rho u times 2hw, it is uniform, and this is the Vx rho v dot n dA. On surface 2, what is Vx? Vx is equal to u of y. Rho v dot n dA will become rho times u of y dy times w, and y will go from minus h to h. Is this clear? So, what we have done is, this was our control volume, I choose an elemental area dy. This velocity is u of y. So, now Vx becomes u of y, rho is rho, v dot n becomes v is u of y, dot n is plus 1 and dA is dy multiplied by the width, and we integrate this from minus h to h, that is what will give us this. Will this give us the right answer? Well, I am asking this, so possibly the correct answer will not come just from this. What would I have missed? Is there something I am missing? And remember, what I have told you is that you have to always ensure that mass balance is satisfied. If you have to ensure mass balance is satisfied, then so first before using this we should have gone for mass balance. And it is very clear that the amount of fluid which is going in from surface 1 is not equal to the amount of fluid which is coming out from surface 2, because clearly if this rectangle area u times 2h should have been equal to the same area on 2y, but capital the small u of y, we know there is a defect. So, therefore, there is some mass, this mass coming out at 2 is not equal to mass coming out at 1. M2 dot is not equal to M1 dot, and that means because this mass is less, if this is 3 and 4, M3 dot and M4 dot is not equal to 0. This is what mass balance tells me, some mass has to leave from surfaces 3 and 4. And once we account for that and make some reasonable approximation, we will be able to get the answer. And in this case, while this mass which is leaving from 3 and 4, most likely its velocity will be in the y direction. But since this area is very large, the y component of velocity will be there, but it will not be 0, it will be some number. But what do you think is the x component of velocity on 3 and 4? On this top surface and bottom surface, what should be a reasonable approximation for x component of the velocity? And clearly x component of velocity here is capital U, and on this top end at the exit it is also capital U. So, a reasonable approximation will be that x component of velocity on 3 and 4 is equal to capital U, and we have this term integral Vx rho v dot n dA. So, on 3 and 4 together, this term will be equal to capital U, this is Vx, it is constant. So, we pull it out of the integral, and rho v dot n dA on surfaces 3 and 4, and together this will be equal to m3 dot plus m4 dot, and this we will be able to get from mass balance, and we do all these, club all this together, and we get our answer. So, this is how we can solve this problem, and this tells us the importance of mass balance which is there. Had we missed out mass balance, we would have got a wrong answer, we would have got a contribution only from these two terms. So, things like this we have to be careful about when we solve these problems. In the next class, we will be looking at the energy equation for a control volume, and this is what is going to give us the Bernoulli's equation. So, this we will do in the next class. Thank you.